heart of a distant galaxy lies Holm 15A, a black hole so massive it defies everything we thought we knew about gravity. How could something this enormous even exist today? We'll uncover the story behind the heaviest black hole in the observable universe. If you enjoy exploring cosmic mysteries, please like, subscribe, and share. And tell us in the comments, what do you think could lie beyond its event horizon? Thank you for watching. Across the deep field of the southern sky, far beyond the reach of any naked eye, lies a vast collection of galaxies bound together by gravity. This is the galaxy cluster known as AB, a structure so large that even light moving at nearly 300,000 kilometers takes hundreds of millions of years to cross it. Within its crowded boundaries, hundreds of galaxies drift through a haze of invisible matter. Their combined mass, woven into an immense gravitational web, the cluster sits in the cosmic neighborhood, often described as the local universe, about 700 million light-years away from Earth. From this distance, even its brightest members appear only as faint points of light to ordinary telescopes, yet together they form one of the most massive and intricate systems known within that range. Around these galaxies lies a sea of hot gas that fills the spaces between them, a diffuse medium heated to tens of millions of degrees. It glows faintly in X-rays detected only by sensitive instruments in orbit, revealing the unseen pressure that holds the cluster in balance. This gas, called the intracluster medium, is composed of hydrogen, helium, and traces of heavier elements expelled by ancient stars. Though nearly weightless compared to the galaxies themselves, it extends so far and carries so much energy that it outweighs all the visible stars combined. Every motion within the cluster occurs inside this hot and turbulent envelope. Each galaxy within Able 85 is like a single cell in a greater organism drifting slowly within the collective pull of dark matter that dominates the cluster's mass. Dark matter cannot be seen or touched, but its presence is measured by the way it bends light from more distant galaxies, an effect known as gravitational lensing. The shape of that bending shows that nearly 90% of the cluster's total weight is invisible without it. The individual galaxies would have long since flown apart. Instead, they remain in a slow dance, colliding and merging over billions of years, exchanging gas and stars in encounters that shape their internal structures. The densest region of this cluster, where the greatest number of galaxies have converged, lies near its center. There, the gravitational well deepens sharply, pulling more matter inward, creating a zone where interactions are constant and violent over cosmic timescales. It is here that the largest and most luminous member of Able 85 has formed a galaxy so extended and diffuse that it seems to blur into the surrounding cluster light. Astronomers classify Able 85 as a rich cluster, meaning it contains more than 100 confirmed galaxies bound in a common halo. Its overall shape, mapped in X-rays, is roughly elliptical, with smaller groups of galaxies feeding into it along filaments of the cosmic web. These filaments are the threads of the universe's large-scale structure, where matter gathers under gravity into nodes, clusters, and superclusters. Able 85 occupies one such node connected by tenuous bridges of gas and dark matter to other clusters tens of millions of light-years away. The scale of this pattern defies human sense. Yet every component follows the same underlying physics of attraction and inertia. Each orbit, each fall, each collision within Able 85 expresses the slow unfolding of gravitational time. In this environment, the lives of galaxies are not measured in years or centuries, but in epochs that last hundreds of millions of years. The overall mass of Able 85 has been estimated to exceed a quadrillion times that of the Sun. Inside this colossal structure, galaxies interact not as isolated islands, but as drifting continents in a shared gravitational sea. The smaller ones are gradually drawn toward the central region, where tidal forces stretch and tear them apart. Their stars are scattered into long streams that wrap around the cluster's core, forming diffuse halos of light. Gas stripped from their interstellar regions falls into the hot intracluster medium, where it is heated and dispersed. Over time, these processes enrich the cluster with heavy elements, turning it into a vast chemical reservoir from which new stars and galaxies may later form. Yet, near the cluster's center, the environment becomes too extreme for ordinary star formation. Temperatures rise, densities fall, and the radiation field from massive galaxies suppresses the cooling of gas. What remains is a quiet but immense brightness from billions of ancient stars, many of which formed in the universe's earliest eras. Seen through large telescopes, Able 85 reveals a tapestry of elliptical galaxies with smooth, featureless shapes. Spiral galaxies like the Milky Way are rare here. The high rate of past collisions has erased their delicate arms, leaving behind the more spheroidal forms typical of cluster core. Among these lies one galaxy that outshines and outweighs all the others, Holm 15A. It occupies the exact center of the cluster's gravitational potential, marking the place where matter has been gathering for billions of years. This type of galaxy is known as a brightest cluster galaxy, or BCG, a title given to the most massive member of a cluster and often to the one hosting its central supermassive black hole. Holm 15A's outer envelope of stars merges almost seamlessly with the diffuse intracluster light, making it difficult to define where the galaxy ends and the cluster begins. When astronomers study Able 85 in different wavelengths, visible light, X-rays, and radio, they find that Holm 15A coincides with the center of the cluster's X-ray emission. That alignment indicates that the galaxy rests at the very bottom of the gravitational well, surrounded by the densest part of the hot gas atmosphere. The gas slowly cools and drifts inward over immense periods, providing a potential source of fuel for the galaxy's nucleus. However, observations show little sign of the violent radiation that such inflow might produce, suggesting that the central black hole lies in a quiescent state, accreting only minimal amounts of matter. This balance between the energy output of the nucleus and the cooling of the surrounding gas is delicate, often regulating the evolution of the entire cluster core. Able 85's environment is thus both crowded and empty, crowded with galaxies, but empty of cold gas and new stars. The cluster's light is dominated by old stellar populations that shine with a reddish hue, marking their age. These stars orbit slowly, bound in the extended gravitational field of the cluster rather than any single galaxy. When viewed in aggregate, their motion traces the underlying potential, mapping the unseen mass that holds everything together. The faint arcs of gravitational lensing visible around the cluster offer further evidence of that hidden structure. Through these subtle distortions, astronomers can reconstruct a distribution of dark matter, revealing a concentration at the center, consistent with the position of Holm. In this way, the entire cluster converges upon a single point of equilibrium. Able 85 is not a chaotic swarm, but a system in long-term balance, its many components orbiting a shared center of gravity. The galaxies may drift, merge, or fade, but the gravitational focus remains constant. Over time, matter flows inward, Energy radiates outward, and the central mass deepens. Holm 15A has grown within this environment as both a product and an agent of the cluster's evolution. Every galaxy that has fallen toward the center, every tidal encounter, every stream of stars torn from a smaller companion has contributed to the building of this dominant core. What began as separate systems scattered across the young universe has coalesced into a single vast assembly. At the center of Able 85, the luminous mass of Holm 15A dominates the surrounding space like a continent of stars, adrift in a cosmic sea. From Earth, its light reaches telescopes as a faint smudge. But in reality, the galaxy spans hundreds of thousands of light years wider than the Milky Way and far more massive. It is an elliptical galaxy lacking the spiral arms or dust lanes familiar in younger systems. Its shape is smooth, extended and faint at the edges, as if starlight itself thins into the darkness. Every part of Holm 15A testifies to an ancient origin and a long history of mergers that have stripped away structure, leaving a single vast spheroid of old stars. This kind of galaxy, called a brightest cluster galaxy, grows at the intersection of cosmic filaments, where matter flows inward from every direction. Over billions of years, it has absorbed smaller galaxies, drawn toward the cluster's core, each collision adding to its mass and expanding its diffuse halo. The light from these merges remains visible as faint envelopes stretching far beyond the galaxy's main body, forming an extended glow that blends with the cluster's background. Astronomers describe Holm 15A as chord, meaning that its surface brightness diminishes sharply toward the center. Instead of growing brighter toward the core as most galaxies do, it becomes dimmer, leaving an enormous region with surprisingly little starlight. This is one of the largest such cores ever measured, spanning tens of thousands of light years, large enough to engulf the entire Milky Way. The absence of central light is not emptiness, but evidence of profound gravitational events. When galaxies of comparable mass merge, the supermassive black holes at their centers spiral toward each other, forming a binary pair. Their combined gravity flings nearby stars outward in 3 dimensions, scouring the core and leaving behind a low-density region. Repeated merges amplify the effect, enlarging the evacuated zone each time. Holm 15A's vast core suggests that its history includes many such collisions. The stars that remain orbit at large radii, their motions dominated by the collective mass of the galaxy rather than by the pull of any single object. In optical images, this produces an impression of light that fades smoothly inward only to fall away too quickly near the center. For observers accustomed to galaxies with bright compact nuclei, the effect appears unnatural, almost hollow. The outer envelope of Holm 15A emerges with the intra-cluster light of Able 85 so gradually that it is difficult to define where one ends and the other begins. This diffuse boundary marks the region where the gravitational influence of the galaxy overlaps with that of the cluster as a whole. Stars here are only loosely bound. Some are shared between the galaxy and the surrounding cluster, drifting through space in long, faint arcs. These intergalactic stars form a kind of bridge between galaxies, evidence of tidal interactions that have unfolded over cosmic time. Their combined light, faint but measurable, gives the cluster core its soft, continuous glow. Holm 15A stands at the center of this glow, like a slow-burning ember, its starlight pale, and even its features blurred by distance and time. The color of Holm 15A reveals its age. Most of its stars are old, red, and low in mass, formed long ago when the universe was younger and denser. The blue light of young stars is almost absent, confirming that star formation has ceased. The reason lies partly in the scarcity of cold gas. Any gas that once cooled to form new stars has either been heated by the cluster's hot atmosphere or swept away by earlier bursts of nuclear activity. Without cold material to condense, the galaxy cannot form new generations of stars. It glows instead with the collective light of billions of aged suns, each nearing the end of its long life. The surface of the galaxy is smooth when viewed through telescopes, showing no dust lanes or sharp features, only the gentle gradient of diminishing brightness. The stellar population of Holm 15A moves in complex patterns that reflect its immense gravitational potential. Near the outer region, stars orbit with speeds of several hundred kilometers as, tracing elliptical paths that weave through the galaxy's faint outer halo. Closer to the center, the orbits become more chaotic, influenced by the combined mass of the stellar body and the unseen black hole that lies at the core. Astronomers measure these motions through spectroscopy, observing the broadening of absorption lines in the galaxy's light. The width of those lines reveals the range of stellar velocities, which in turn indicates the total mass enclosed within a given radius. In Holm 15A, the broadening is extreme, suggesting a gravitational field of extraordinary strength. This galaxy's dimensions are difficult to comprehend. From its outer edge to its faint center, light takes hundreds of thousands of years to travel. Within that span, trillions of stars orbit through diffuse layers, their combined brightness forming the faint hazy structure visible in deep images. The overall mass of Holm 15A is estimated to be several trillion times that of the Sun, and its halo extends outward until it blends into the cluster's general field. Though its density is far lower than that of smaller, more compact galaxies, its total size makes it one of the most massive known elliptical systems in the local universe. The gravitational force binding it is immense, yet distributed so smoothly that no single point stands out, except the hidden nucleus at its center. And from a distance, Holm 15A appears calm and unchanging, but every particle of gas and every star within it moves according to the laws of gravity. The galaxy is a system in motion, even if its pace is beyond human perception. Over the course of billions of years, faint streams of stars will continue to fall inward from the cluster, merging with the outer halo and increasing its size even further. Meanwhile, the innermost regions remain nearly motionless in appearance, dominated by the unseen presence that shapes the orbits of nearby stars. The faintness of the core draws attention not only because it is empty of light, but because it hints at something far heavier than starlight alone could account for. Astronomers studying Holm 15A often describe it as diffuse, extended, and extreme. Its structure breaks the usual correlations between brightness and size observed in most galaxies. This central deficit of light, when plotted against radius, exceeds predictions by large margins. This departure makes it a valuable case study for understanding how galaxies evolve through mergers and how their central black holes grow in tandem. Every faint contour, every smooth curve of brightness carries information about past collisions. The current shape of the galaxy is not the product of a single event, but of many overlapping histories. Each merger redistributed mass, altered orbits, and reshaped the core, slowly building the diffuse forms seen today. In the balance between mass and light, Holm 15A represents the mature state of galactic evolution within a rich cluster environment. It has consumed or merged with most of its neighbors, exhausted its gas, and reached a kind of gravitational calm. Yet within this apparent stillness lies the key to one of the most extraordinary measurements ever made. At the exact center of the dim core, invisible to direct view, resides a concentration of mass so large that it dominates not just the galaxy, but the surrounding cluster light itself. Its presence is revealed only through motion, the small but measurable accelerations of the stars that orbit near the middle. The discovery of this hidden mass would later define Holm 15A as one of the most remarkable galaxies. Deep within the faint glow of Holm 15A lies a region unlike any other in the cluster, an immense dimly lit core where the usual density of starlight falls away to almost nothing. Most elliptical galaxies grow brighter toward their centers, but this one reverses that rule. The light from billions of stars fades into a hollow space spanning tens of thousands of light years, creating one of the largest known galactic cores in the observable universe. Observers who study its brightness profile find that the decline toward the center is far too steep to be explained by normal stellar distribution. It is as though an unseen hand has scooped out the middle of the galaxy, scattering stars outward and leaving behind a ghostly void. Through powerful telescopes, the central region appears smooth and almost featureless, glowing faintly against the background sky. The stars that remain within it move swiftly, bound by an invisible force far greater than their combined mass. Each orbit carries the trace of gravitational memory shaped by collisions that took place long before human life existed on Earth. This unusual emptiness was one of the first clues that Holm 15A hides something extraordinary at its center. The process that carves such cores is linked to the violent history of galactic mergers. When two massive galaxies collide, their central black holes sink toward the middle of the new system, forming a binary pair. The immense gravity of that pair flings nearby stars away, each encounter ejecting material and enlarging the hollow region. The more merges occur, the deeper and broader the core becomes. Holm 15A's vast central gap suggests that many such events have taken place, each adding to the sculpting of its inner light. In effect, the black holes act as cosmic excavators, reshaping the galaxy's interior through the combined energy of their orbit. Once the black holes themselves merge, the resulting object settles at the center, and the surrounding stars carry the imprint of that encounter for billions of years. The density of starlight in this region is extraordinarily low compared to the outer galaxy. Instead of a crowded nucleus, there is a diffuse glow that fades almost imperceptibly into the surrounding halo. The stars that do remain follow elongated, sometimes chaotic orbits, moving through a gravitational field dominated by the unseen mass of the central black hole. Spectroscopic studies show that their speeds rise steeply toward the middle, reaching hundreds of kilometers, too fast to be maintained by starlight alone. These motions, when modeled, reveal the gravitational fingerprint of a central object, weighing tens of billions of solar masses. Yet the black hole itself emits almost no light, its presence betrayed only by the behavior of the stars around it. The sheer scale of the lightless region is difficult to convey. If the Milky Way were placed inside Holm 15A's core, our entire galaxy, from its spiral arms to its bright nucleus, would fit comfortably within the faint central cavity. No gas clouds fill the space, no dust lanes obscure it, only the residual glow of distant stars remains. For astronomers, this emptiness is a valuable map of the galaxy's history. The absence of stars where they would normally concentrate tells a story of gravitational clearing, a record of how energy from merging black holes reshaped matter on a colossal scale. Every low-density region marks the space once occupied by ejected stars, each driven outward by a brief but immense gravitational interaction. The combined effect of millions of such ejections carved the smooth depression seen today. Photometric surveys reveal that Holm 15A's core is not sharply bounded, but transitions gradually from low brightness to the higher density of the outer regions. The change follows a smooth mathematical curve, known as a chord profile, a function used to describe galaxies whose centers have been depleted by mergers. In this model, the outer light behaves as expected, while the inner light deviates downward, signaling that something has physically removed stars from the center. Holm 15A's deviation is extreme, even among the largest galaxies. This makes it an ideal laboratory for studying how gravitational dynamics on galactic scales operate when masses reach billions of solar equivalents. Inside the hollow heart, gravity maintains a subtle equilibrium. Though few stars remain, the gravitational pull from the surrounding mass keeps the structure stable. The central black hole exerts the dominant influence, but the outer stellar envelope still contributes significantly to the field. The result is a region where orbits are long, slow, and erratic, overlapping like tangled threads of motion. Over billions of years, these orbits will evolve through weak interactions, but the overall structure will persist, changing only slightly as more stars drift inward or are scattered outward. The faint light seen from this region represents the delicate balance between attraction and emptiness, between what remains and what has been expelled. Infrared observations confirm that little dust or cold gas resides in the core. Without such material, there is nothing to obscure the view, and the starlight seen there is purely the remnant of old populations. The lack of gas also explains the absence of new star formation. Every star visible within Holm 15A's center was born billions of years ago, long before the cluster achieved its current form. Each one now serves as a tracer particle in the gravitational field of the black hole, revealing through motion what cannot be seen directly. The temperature of the surrounding cluster gas, reaching tens of millions of degrees further, prevents any new condensation of material. The core, in this sense, is frozen in both space and time. The morphology of Holm 15A differs from other bright cluster galaxies with smaller cores. In many systems, a faint jet or nucleus indicates an active black hole, but here, no strong emission is detected. The central region emits little in radio or X-ray wavelengths, suggesting that the black hole accretes matter very slowly. Its silence enhances the mystery of the vast cavity it occupies. A dormant engine sits at the heart of one of the largest gravitational wells in the known universe, shaping the motion of everything nearby while remaining nearly invisible. This quietness gives Holm 15A its particular stillness, the sense of an enormous mass resting in perfect balance. Astronomers studying the galaxy describe the light profile with terms like extended envelope, depleted core, and central deficit. Each phrase captures a different aspect of the same physical phenomenon, the displacement of stellar mass caused by the gravitational influence of merging black holes. When the system finally stabilizes after such an event, the result is a galaxy with a faint center and a smooth transition outward. In Holm 15A, this balance has reached its extreme. The lack of light is not a void in the ordinary sense, but a monument to energy exchanged on an unimaginable scale. It marks the spot where gravity has done its deepest work, moving stars like dust until only the heaviest object remained. Even at this scale, the core maintains coherence. Its faint light merges seamlessly with the outer halo, and beyond that, with the cluster's diffuse glow. No boundary separates the galaxy from the environment around it. All belong to the same gravitational continuum. The lightless core, immense and almost motionless, lies at the center of that continuum, an anchor for the motions of countless stars. From afar, it appears calm, a quiet hollow in the midst of surrounding brightness. Up close, it is the domain of relentless gravity, where every orbit bends toward an unseen center, and where the memory of ancient collisions remains written into the shape of space itself. The hollow core of Holm 15A did not emerge by chance. It is the visible memory of a long succession of galactic mergers that have shaped its present form. Across billions of years, Able 85 has acted as a cosmic crucible where galaxies are drawn together under the immense pull of the cluster's gravity. Each approach, collision and fusion, leaves behind subtle traces, gradually transforming smaller systems into larger, more diffuse forms. When two galaxies of roughly equal mass encounter one another, their outer halos begin to overlap first. Stars, gas, and dark matter respond to the rising tidal forces, stretching into bridges and tails that span hundreds of thousands of light years. These features, visible in younger clusters, mark the initial phase of merging. Over time, the galaxies spiral closer, losing orbital energy to gravitational interactions and dynamical friction. A slow braking process caused by the wake each galaxy raises in the surrounding matter. The result is a gradual coalescence that can take more than 1 billion years to complete. When the merger is finished, the two systems become one, their stars redistributed into a new, more massive galaxy. The physics of merging galaxies is complex but predictable in its broad outlines. As the nuclei of two galaxies approach their central black holes, follow suit, sinking toward the common center of gravity. Each carries a cluster of stars and gas bound to it, and their combined mass exerts a growing influence on the new host. When the black holes finally meet, they form a binary pair, orbiting one another at speeds approaching thousands of kilometers. Their gravitational energy ejects nearby stars, flinging them outward in random directions. This process scours out the galactic core, reducing its brightness and creating the vast central hollows observed in systems like Holm 1. In some cases, the black holes eventually merge, releasing gravitational waves that carry energy away from the center and slightly displacing the merged object. If additional mergers follow, the cycle repeats, enlarging the depleted region even further. The scale of Holm 15A's lightless core indicates that this has happened many times, perhaps as many as 10 major mergers over the age of the cluster. The aftermath of these encounters is written into the faint outer halo of the galaxy. Streams of stars stretch across hundreds of thousands of light years, remnants of the smaller systems absorbed long ago. The motions of these streams reveal the gravitational field of the main galaxy and hint at the violent interactions that created them. Many of the absorbed galaxies likely resembled the Milky Way, with spiral arms and ongoing star formation. By the time they joined Holm 15A, their gas was stripped by the cluster's hot, medium, and their structures were shredded by tidal forces. What remained were the long-lived stars that now drift within the larger galaxy's smooth glow. The transformation of structured spirals into featureless ellipticals is a hallmark of such environments. And in Holm 15A, that transformation has reached its end point. As galaxies merge, the energy released by their central black holes can shape the flow of matter across vast distances. During periods of intense accretion, When gas falls rapidly toward the black holes, jets of high-energy particles and radiation can erupt outward, heating the surrounding gas and preventing further cooling. This self-regulating cycle determines how quickly new stars can form. In the dense center of Able 85, the balance is tipped towards stability. The gas that might once have fed new star formation has been heated and dispersed, leaving the core dominated by old stars in the quiet glow of equilibrium. Holm 15A is a product of that equilibrium, massive, quiescent, and stripped of nearly all raw material for growth. The simulations that model such galaxies show that the largest ellipticals grow, not through steady star formation, but through repeated mergers of already mature systems. Each merger increases mass and size while reducing central density. The stars that remain are spread over larger volumes, producing the diffuse profiles observed in brightest cluster galaxies. The cores grow by expansion, not by collapse. In this sense, Holm 15A's hollow center represents the opposite of a typical galactic nucleus. Instead of concentrating matter inward, its history has pushed matter outward, guided by the unseen gravity of its black hole. This reversal of density gives the galaxy its peculiar structure and extreme scale. The gravitational interactions involved in these mergers operate over time, scales far beyond human perception. A single orbit of a star near the outer halo may take hundreds of millions of years. The fusion of two massive galaxies, each containing hundreds of billions of stars, proceeds so slowly that even when viewed in simulation, the process appears almost serene. Yet within that serenity lies enormous violence. Stars are torn from their orbits, flung into intergalactic space, or captured by new gravitational wells. Dark matter halos overlap and merge, deepening the potential that holds the cluster together. Every collision releases energy, reshaping the balance of light and mass in subtle ways. At the cluster scale, these merges are part of a continuous inflow of material. Galaxies drawn from the outskirts of Able 85 fall toward the center, feeding the growth of Holm 15A. Some arrive as compact groups, merging with one another before joining the main system. Others are stripped apart before they reach the core, their stars added directly to the cluster's diffuse light. Over cosmic time, this steady accretion ensures that the central galaxy becomes both the brightest and the most massive. Observations across many clusters confirm this pattern. The central galaxies are always the largest, their size proportional to the cluster's total mass. Holm 15A exemplifies this rule with striking clarity. The effects of these mergers extend beyond the visible light of stars. The hot, intra-cluster gas responds to gravitational compression, heating further as galaxies collide. Shock fronts ripple through the medium, carrying energy outward. In some cases, cavities appear in X-ray maps, where jets from active black holes have cleared bubbles in the gas. Though Holm 15A shows little current activity, traces of older outflows remain imprinted in the cluster's thermal structure. These relics testify to earlier times when the central black hole was more active, feeding on infalling gas and releasing powerful jets that balanced the cluster's cooling. The energy from such events helped maintain the long-term stability of the system, preventing runaway condensation of the gas. What remains today is the quiet phase of this vast cycle. The galaxies that once collided now coexist in equilibrium, moving within a shared gravitational field that changes only slowly. Holm 15A, swollen by its mergers, glows with the combined light of everything it has consumed. Its core, still shaped by past encounters, stands as the signature of cosmic evolution, working on the largest possible scale. The faintness at its center is the imprint of energy exchange through gravity and time. Each vanished galaxy, each dispersed star, and each merged black hole has contributed to the formation of this one immense and tranquil system. The aftermath of those ancient collisions still defines its structure today, a quiet reminder that even the universe's greatest violence eventually yields stillness. At the quiet center of Holm 15A, where starlight fades almost to darkness, lies the most massive and least visible object in the galaxy. No telescope can capture its outline, and no photograph can reveal its source. Yet its presence dominates the entire structure. It is the central black hole, a region of space where gravity is so strong that not even light can escape. Its mass is measured not in millions, but in tens of billions of solar masses, making it one of the heaviest black holes known in the observable universe. Everything nearby, stars, gas, and dark matter, moves under its influence, tracing orbits that mark its position even when it remains unseen. This invisible dominator is both the product and the engine of the galaxy's history, formed through countless mergers and sustained by the steady inward pull of gravity over cosmic time. To understand how such a colossal object rules its environment, astronomers rely on the evidence left in motion rather than in light. The stars near the core move faster than those farther out, accelerating sharply as they approach the invisible center. The same gravitational law that governs planetary orbits around the sun applies here, but the scale is vastly different. Within a few hundred light years of the core, stellar speeds exceed 1,000 kilometers velocities that no other process can produce. The only explanation consistent with these motions is a point-like mass concentrated in the middle, a black hole of extraordinary size. The lightless region that marks its position is not empty. It is the boundary of an immense gravitational well. The influence of this central mass extends far beyond its immediate surroundings. The black hole's gravitational reach affects the entire galaxy, shaping the distribution of stars, controlling the flow of gas, and even influencing the dynamics of the cluster that envelops it. Theoretical models show that when black holes exceed a few billion solar masses, their spheres of influence can stretch across tens of thousands of light years, rivaling the size of smaller galaxies. In Holm 15A, the estimated reach of the central object may exceed the size of our entire Milky Way, meaning that the motions of stars over enormous volumes are subtly guided by this single gravitational source. The invisible object acts as a stabilizing anchor, keeping the diffuse stellar halo bound despite the low density of light. This balance between invisibility and control defines the character of Holm 15. Unlike the bright active cores of quasars, where matter spirals inward and radiates enormous energy, the center of this galaxy remains almost perfectly quiet. There is little sign of gas falling toward the black hole, and without infall there is little radiation. The result is a massive but dormant nucleus, an object of staggering weight that emits almost nothing. This quiet state is typical of giant, elliptical galaxies in mature clusters where most available gas has long since been heated, and the surrounding environment offers little material for accretion. So the black hole endures in silence, governing through gravity alone. The relationship between the black hole and the galaxy around it is one of mutual shaping. During periods of intense activity in the distant past, Outbursts from the growing nucleus would have heated the cluster's gas, preventing it from cooling and forming new stars. Those feedback events regulated the pace of galactic growth, setting limits on how massive the central regions could become. Over time, as the supply of cold gas diminished, the black hole itself entered a phase of quiescence. Now the energy that once erupted outward is stored in gravitational potential, and the core glows only with the ancient light of stars, unaffected by recent activity. The mass of Holm 15A's black hole challenges the limits of known formation models. Most theories predict that even in the densest environments, central black holes should not exceed a few billion solar masses. To reach tens of billions, a galaxy must undergo repeated merges, each event combining two massive black holes into one larger object. The energy released during those merges ripples through space as gravitational waves, carrying away momentum and allowing the merged system to settle at the center. Holm 15A's history implies a long succession of such events, with each generation building upon the last. The black hole that remains is therefore a living record of the cluster's entire assembly process. Measuring such mass requires precision far beyond direct imaging. Astronomers analyze the absorption lines of starlight across the galaxy's face using high-resolution spectroscopy to trace the subtle changes in wavelength caused by stellar motion. These data feed into complex dynamical models that simulate how stars would behave under different gravitational fields. By adjusting the model until it reproduces the observed velocities, researchers can infer the mass of the central object. In Holm 15A, the results consistently point to a value tens of billions of times greater than the Sun's. Though the exact figure varies depending on assumptions about orbital shapes and inclination, even the lowest estimates place it among the largest black holes ever measured direct. Despite this immense power, the black hole is invisible at all wavelengths. No jets pierce the surrounding space. No luminous disk circles its edge, and no bright X-ray source betrays the presence of hot and falling matter. Instead, its signature is purely gravitation. It shapes the galaxy's internal dynamics as surely as a hidden planet shapes the orbits of moons. The quietness itself is revealing. It indicates that the central engine has reached a stage of long-term stability, having consumed or expelled nearly all the gas that once fed it. What remains is equilibrium, a balance between gravity, pressure, and motion that may last for billions of years. The concept of an object that dominates by absence is one of the most striking features of cosmic structure. In Holm 15A, the black hole's silence contrasts with its authority. The remnant stars continue their slow revolutions, tracing patterns that echo the shape of the unseen potential. Each orbit is an expression of gravity's geometry, determined entirely by the mass hidden at the core. To imagine the scale of its event horizon is to contemplate a sphere, so vast that light itself would take days to circle it, yet so small compared with a galaxy that it occupies only a tiny fraction of the total volume. Still, that fraction governs. The invisible dominator does not simply exist at the center. It defines what the center means. Without it, Holm 15A would lose its cohesion. Its stars would drift apart, and its diffuse halo would gradually unravel into the cluster medium. The black hole's presence ensures continuity, maintaining the galaxy's structure against the slow diffusion of time. Though unseen, it is the gravitational heart of the system, the point toward which all motion tends. It neither shines nor stirs the gas around it. Yet its influence is absolute. Across tens of thousands of light years, the faint light of ancient stars bends subtly toward this silent core. In that curvature of motion, the galaxy's shape is preserved, and its itis remains bound to the unseen weight that lies at its center. The immense black hole at the center of Holm 15A cannot be observed directly, yet its presence is measured with remarkable precision. In the absence of light, astronomers rely on motion, for gravity reveals itself through the way it bends and accelerates matter. To measure an object that emits no radiation, they observe the behavior of the stars and gas around it. Each point of light within the galaxy's faint core moves according to the gravitational pull it feels. And by mapping those motions, scientists can infer the mass of what lies at the center. This method, called stellar dynamical modeling, transforms starlight into a record of motion. The shifts in wavelength of spectral lines, red or blue, depending on movement toward or away from Earth, provide a direct measure of velocity. When thousands of such measurements are combined across the face of the galaxy, they form a map of speed and direction, a silent diagram of how space itself is curved by mass. The process begins with observation. Telescopes on the ground collect the faint light from Holm 15A, dispersing it through spectrographs that split it into its component colors. Each pixel in the resulting image holds information about the motion of stars within that part of the galaxy. The European Southern Observatory's Very Large Telescope was among the first to capture such data using its MUSE instrument to record two-dimensional spectra across the central region. The results showed broad absorption lines, evidence that stars in the core moved at extraordinary speeds. These lines were compared with models of how light would appear if the galaxy contained only visible matter. The discrepancy was vast. The observed motions required a gravitational field far stronger than could be explained by starlight alone. To interpret these data, astronomers build detailed simulations that calculate how stars would move under different mass distributions. The models include the effects of both the stellar population and any central black hole. By adjusting the mass of the unseen component and comparing the simulated velocities with the observed ones, the researchers identify the value that best reproduces reality. In Holm 15A, this process led to an astonishing result. The central object's mass appeared to be roughly 40 billion times that of the Sun, making it one of the most massive black holes ever detected through direct dynamical methods. Such a number immediately drew attention, not only for its magnitude, but for what it implied about galaxy formation. If correct, it meant that Holm 15A's black hole accounted for a significant fraction of the entire galaxy's stellar mass, an unusually high ratio that defied expectations from previous studies. The precision of this result depends on the assumptions built into the model. Astronomers must account for the galaxy's orientation in space, the shape of its orbits, and the contribution of dark matter. These factors influence how velocities appear when projected along our line of sight. To refine the measurement, later studies used new instruments with higher resolution. The Keck Observatory's Keck Cosmic Web Imager allowed scientists to model the galaxy in 3 dimensions rather than 2, accounting for triaxial orbits that more accurately describe real stellar motion. The updated calculations yielded a slightly smaller but still immense mass of about 22 billion solar masses. Though lower than the original estimate, it confirmed Holm 15A's black hole as one of the largest known in the nearby universe. The difference between these numbers reflects not uncertainty in the reality of the black hole, but the inherent complexity of modeling such vast systems. Behind every figure lies an intricate interplay of physics and observation. The gravitational influence of the black hole must be distinguished from that of the surrounding stars, whose own mass contributes to the total potential. In regions far from the center, the stars dominate. Near the core, the black hole takes control. The radius at which these two influences balance defines the black hole sphere of influence, a crucial region for measurement. In Holm 15A, this radius extends over several thousand light-years, so large that it encompasses a significant portion of the visible galaxy. Within this domain, stellar motions rise sharply, a pattern that no model without a central mass can reproduce. Even with modern technology, the data are faint and delicate. Each observation requires long exposures to collect enough photons from the distant galaxy. Atmospheric turbulence blurs the light, so adaptive optic systems adjust mirrors in real time to correct for distortion. The resulting spectra are then processed, calibrated, and combined to produce velocity maps. These maps reveal gradients, smooth changes in speed from one side of the galaxy to the other that signify rotation and random motion. From these patterns, astronomers derive not only the black hole's mass, but also the anisotropy of stellar orbits, a measure of how orderly or chaotic their paths are. The stars of Holm 15A show little rotation and high-velocity dispersion, consistent with a history dominated by mergers rather than calm evolution. The reliability of such measurements also depends on distance. Small errors in the estimated distance to the galaxy translate directly into uncertainties in mass. Fortunately, Able 85's distance has been measured through several independent methods, including redshift and cluster scaling relations, giving confidence in the derived values. Still, the margin of error remains large, because even the best models simplify reality. Galaxies are not perfect spheres, and their stars do not follow identical orbits. Despite these challenges, independent teams using different datasets converge on the same conclusion. Holm 15A's central black hole is among the most massive directly measured in the local universe. These measurements represent the culmination of decades of development in observational astronomy. Early studies of smaller galaxies established the relationship between black hole mass and the velocity dispersion of the surrounding stars, known as the M-sigma relation. According to this correlation, galaxies with faster stellar motions host heavier black holes. Holm 15A sits far above the expected line, its black hole far more massive than its stellar velocity dispersion would predict. This deviation implies that the processes governing the growth of the largest galaxies may differ from those that shape smaller ones. Instead of gentle accretion, the history of Holm 15A may have been dominated by violent mergers that rapidly increased both the size of the galaxy and the mass of its central object. The success of dynamical measurement in a system as distant as Able 85 demonstrates how far astronomical technique has progressed. From faint redshifted light, researchers extract the signatures of motion across thousands of light years, reconstructing a gravitational landscape invisible to any camera. The ability to weigh an unseen object tens of billions of times heavier than the sun from a point of light smaller than a pinhole represents a triumph of observation and theory. Though the black hole itself remains forever hidden, the evidence of its presence is written clearly in the language of motion. The unseen becomes measurable, and gravity, though silent, leaves a trace strong enough to define the center of an entire galaxy. In that trace, the invisible becomes known not through sight, but through the precise geometry of its influence. When the first detailed measurements of Holm 15A's central region were completed, the astronomical community was confronted with a number so extraordinary that it seemed to stretch the limits of known galactic physics. In the year 2019, a team of researchers analyzing data from the European Southern Observatory announced a dynamical mass estimate of roughly 40 billion solar masses for the black hole at the heart of the galaxy. The number was derived from a combination of spectroscopic observations and computer models designed to reproduce the observed motion of stars within the inner regions. This value, if correct, placed Holm 15A's black hole not just among the largest ever measured, but possibly at the very top of the known mass scale for any black hole in the local universe. It was a result that demanded both astonishment and caution because the methods used, while rigorous, required assumptions about the geometry and orientation of the galaxy that could influence the outcome. Nevertheless, the finding was immediately recognized as one of the most remarkable discoveries in modern astrophysics. The observations behind that measurement were collected with the MUSE spectrograph on the Very Large Telescope in Chile. MUSE, short for Multi-Unit Spectroscopic Explorer, is capable of capturing detailed spectral information for every point in its field of view, creating what scientists call an integral field data cube. Each pixel in this cube represents a location on the sky and carries a complete spectrum of light. By examining how those spectra shift in wavelength, researchers can measure the velocity of stars moving toward or away from us. In Holm 15A, these velocity shifts were broad and smooth, indicating a high degree of random motion. Stars near the galaxy's center moved faster than those farther out, and the rate of increase was steep enough to require an immense concentration of mass at the core. From these measurements, the team built a series of dynamical models, each representing a slightly different distribution of stars and dark matter. They adjusted the black hole's assumed mass until the simulated velocity field matched the one observed. The best fit corresponded to a central object weighing approximately 40 billion times the mass of the Sun. That number was consistent with the galaxy's extraordinarily large core, suggesting that multiple generations of mergers had scoured out its center. The result was quickly compared to those of other extreme systems, such as the black holes in M87, NGC 4089, and the quasar TN 618, all of which fall in the range of billions to tens of billions of solar masses. Yet Holm 15A's value exceeded them all, making it a candidate for the heaviest directly measured black hole in the nearby universe. The implications of such mass were profound. If the estimate was accurate, then the black hole alone would account for several percent of the total stellar mass of Holm 15A, a ratio far above that predicted by standard scaling relations between black holes and their host galaxies. Those relations, established through decades of observations, suggest that black holes typically represent about 1/10 of a galaxy's stellar mass. Holm 15A appeared to defy that pattern by more than an order of magnitude. The discovery forced theorists to reconsider how the largest galaxies and their central black holes evolve, and whether different physical processes dominate at such extreme scales. It also raised questions about the limits of black hole growth. Could nature produce even heavier objects? Or did Holm 15A represent the upper boundary of what gravity and time could achieve in a single system? In the month that followed, independent researchers began to re-examine the data, testing the robustness of the result. Some noted that the modeling technique used a spherical assumption for the galaxy's structure, which might not fully capture its true three-dimensional shape. Others pointed out that the limited spatial resolution of the observations could blur the inner velocity field, leading to an overestimate of the black hole's mass. Despite these caveats, the general conclusion remained that Holm 15A's nucleus contained an object of unprecedented size. Even if the mass was smaller by a factor of 2, it would still exceed almost every other direct measurement. The result stood as a milestone, representing the first clear evidence that black holes could grow beyond 30 billion solar masses through the combined effects of mergers and prolonged accretion. The announcement drew attention not only for its numerical value, but for what it revealed about the universe's extremes. In press releases and scientific meetings, researchers emphasized that this was not an exotic or distant quasar blazing from the early universe, but a nearby galaxy within a well-studied cluster. The existence of such an enormous black hole so close in cosmic terms suggested that these objects might be more common than previously thought, hidden inside the faint cores of giant ellipticals that have long since ceased active accretion. Holm 15A thus became a template for understanding the final evolutionary stage of the most massive galaxies, those that had consumed all available fuel and settled into quiet gravitational dominance. At the time of the discovery, the data represented the limits of available instrumentation. MUSE provided a clear view of the inner velocity field, but finer details remained beyond reach. The team could not directly observe the black hole sphere of influence, which in Holm 15A extends over several thousand light-years, but subtends only a fraction of an arcsec. Still, by combining kinematic data with surface brightness profiles from high-resolution imaging, the researchers constrained the model as tightly as possible. The remarkable agreement between observed and simulated velocity dispersions lent strong confidence to the inferred mass. For astronomers accustomed to measuring black holes in millions or a few billion solar masses, the jump to 40 billion was both exhilarating and disorienting. Theoretical work quickly followed, attempting to explain how such a massive black hole could form. One possibility was that Holm 15A's black hole grew through successive merges of smaller ones during the early assembly of Able 85. Each collision between galaxies would bring a pair of central black holes that eventually merged into a larger object. Over billions of years, this process could build the colossal mass now observed. Another idea proposed that the galaxy's central potential well allowed unusually efficient accretion of gas during its early history, producing rapid growth before the cluster environment became too hot and diffuse. Regardless of the mechanism, the end result fit neatly within the broader picture of hierarchical structure formation, where small systems merge to make larger ones, and the largest lie at the centers of the deepest gravitational wells. The 40 billion solar mass figure soon entered the scientific literature as both a reference point and a challenge. It stood as the upper bound of direct measurement beyond which few systems had yet been confirmed. For the public, the discovery captured the imagination, a single object so massive that it outweighed entire galaxies. Yet for astronomers, the result was an invitation to refine, test, and question. Could the measurement be improved with higher spatial resolution? Could new instruments resolve the motions of stars even closer to the center? Such questions would eventually lead to a new generation of studies, culminating years later in revised estimates that would bring the mass downward, but not diminish the significance of what had been learned. In the quiet after the announcement, Holm 15A remained unchanged. A faint glow in the constellation Serpens, its immense core continuing its silent orbit within the cluster. The light that revealed its secret had traveled for hundreds of millions of years before reaching Earth, carrying within it the subtle shifts that betrayed the presence of an invisible titan. Whether 40 billion or slightly less, the measurement marked a turning point in our understanding of cosmic extremes. For the first time, astronomers had weighed an object whose gravity alone could hold a galaxy together, a black hole so vast that it blurred the distinction between individual and collective mass. In that single number lay the record of everything the galaxy had been and everything gravity had ever gathered into its quiet, lightless heart. In the years after the astonishing announcement that Holm 15A might contain a 40 billion solar mass black hole, astronomers sought to verify the claim with sharper data and more refined models. The challenge was immense. Measuring motion in a galaxy hundreds of millions of light years away requires extraordinary precision, and even slight assumptions about geometry or viewing angle can shift results by billions of solar masses. Yet technology and method added. In 2025, researchers using the Keck Observatory's Keck Cosmic Web Imager turned their attention once more to the galaxy's dim center. Keck's adaptive optics and higher spatial resolution allowed them to see the core in finer detail than ever before. They collected an array of spectra across the inner few arcseconds, capturing the Doppler signatures of countless stars. When these data were compared with new triaxial orbit-based models, representations that allow stars to follow non-spherical paths within the galaxy's potential, a new picture began to emerge. The mass of the central black hole was revised downward to about 22 billion solar masses, still one of the largest directly measured values in the local universe, but smaller than the first claim. The revision did not undermine the earlier discovery. Instead, it clarified it, replacing astonishment with precision. Triaxial modeling offered a major improvement over the simpler assumptions used before. Earlier analyses treated Holm 15A as roughly spherical, yet few galaxies are truly so. The stars within elliptical systems move along a mix of box-shaped, tube-shaped, and chaotic orbits, each responding differently to gravity depending on their orientation. By allowing these shapes to coexist, the new models could reproduce the observed velocity field more realistically. The Keck data also provided higher signal-to-noise ratios, reducing uncertainties in the measured velocity dispersions. When researchers ran thousands of simulated configurations, the best-fitting solution consistently yielded a black hole mass near 20. This was still an extraordinary figure, nearly 3,000 times the mass of Sagittarius A, the black hole at the Milky Way's center, and comfortably within the range that made Holm 15A one of the most extreme galaxies known. The difference between 40 and 22 billion solar masses illustrated the difficulty of measuring the unseen. In such distant systems, no telescope can resolve individual stars near the event horizon. Instead, scientists infer the mass indirectly from averaged motion. Any deviation in assumed inclination or anisotropy changes the outcome. But even with these uncertainties, the conclusion remained firm. Holm 15A houses a black hole of truly exceptional size, easily among the heaviest, confirmed by direct dynamical measurement. Whether its exact mass is closer to 20 or 40 billion is less important than the broader truth. It reveals that nature builds gravitational objects of nearly unimaginable scale, and that these objects govern the structure of their galaxies in silence. The new Keck observations also provided insight into the shape and size of the galaxy's core. By combining optical data with imaging from space-based observatories, astronomers mapped the light distribution more precisely than before. The depleted region at the center was confirmed to be immense, extending roughly 15,000 light-years from side to side. Within it, the stellar density dropped by nearly an order of magnitude compared to the outer halo. The structure fit perfectly with the idea of multiple mergers and black hole scouring. Each event would have ejected stars from the nucleus, leaving the faint depression visible today. The core's brightness profile matched that of other giant ellipticals, but on a scale roughly twice as large. This consistency across very different systems strengthened the case that Holm 15A's structure represents an amplified version of a common process, rather than a unique anomaly. The downward revision of the black hole mass carried implications for cosmology as well. The earlier 40 billion estimate had seemed to challenge the established correlations between galaxy mass and black hole mass, suggesting that Holm 15A lay far above the expected relation. The new value brought it somewhat closer, though still high. This alignment reaffirmed the idea that even at the extreme upper end, galaxies and their central black holes co-evolve according to similar rules. When galaxies merge, their black holes merge. When gas inflows feed one star formation and the host is suppressed by the energy released, the balance between these processes keeps the ratio roughly stable. Holm 15A may simply represent the farthest reach of that equilibrium. The revised models also revealed subtler details about the stellar dynamics near the core. The velocity map displayed milder symmetries, small deviations from perfect circular symmetry, indicating that the galaxy may still carry the residual imprint of its most recent merger. In one direction, stars showed slightly higher velocity dispersion, perhaps tracing the remains of an orbiting remnant. Over the next few billion years, such irregularities will likely fade as gravitational relaxation smooths the system. For now, they provide a glimpse into how equilibrium is achieved after cosmic violence. Even in its calm appearance, Holm 15A is still settling from ancient turbulence. In X-ray observations taken by the Chandra Observatory, the region surrounding the galaxy remained faint, but not entirely silent. A weak point source at the center hinted at low-level accretion, matter slowly spiraling inward toward the black hole, but releasing little radiation. The energy output was millions of times lower than that of active quasars, confirming that the nucleus is now in a dormant phase. This inactivity may persist for billions of years unless new material is supplied. The intracluster gas around Abel 85 is hot and thin, and only a fraction of it can cool and sink inward. Thus, Holm 115A's black hole endures as an immense but sleeping power, radiating almost nothing while holding the galaxy together through its invisible gravity. For the scientific community, the revision marked an evolution in understanding rather than a contradiction. The initial estimate had demonstrated what was possible with state-of-the-art instruments. The Keck study refined those possibilities. Together, they charted the frontier of direct measurement in extragalactic astronomy. Both results required vast observing time, complex modeling, and high-performance computing to simulate millions of stellar orbits. That effort turned faint light into knowledge of a gravitational object that cannot be imaged by any telescope. Holm 115A became a benchmark, its data serving as a test case for improving dynamical methods that will later be applied to other massive galaxies. The idea that a single object could contain tens of billions of solar masses is still almost beyond comprehension. If such a black hole were placed at the center of the Milky Way, Its event horizon would extend beyond the orbit of Pluto, and its influence would encompass the entire solar system many times over. Yet within the scale of Holm 15A, it remains a compact feature, occupying only a minute fraction of the galaxy's total diameter. This contrast between small physical size and enormous gravitational reach defines the paradox of black holes. They're both tiny and vast, local and cosmic, singular and collective. The more precisely they are measured, the more fully that paradox reveals itself. By 2025, consensus had begun to form. The black hole at the heart of Holm 15A weighs roughly 22 billion solar masses, give or take a few billion depending on model choice. It ranks among the heaviest ever confirmed in the nearby universe, rivaled only by those in the brightest cluster galaxies of similar scale. Its surrounding core remains one of the largest known as a cavity carved by the combined energy of mergers over cosmic time. These findings anchor Holm 15A as a cornerstone in the study of extreme galactic systems, a natural laboratory where the limits of gravitational physics can be observed, not in theory but in light itself. The refinement from 40 to 22 billion does not diminish its significance. It underscores the power of observation to turn awe into understanding, replacing mystery with measured reality, while leaving the sense of wonder untouched. When Holm 15A's extraordinary black hole was confirmed, astronomers naturally turned to compare it with other cosmic giants. The known universe hosts many supermassive black holes, yet only a few approach the same scale. These rare objects occupy the centers of the brightest cluster galaxies and the most powerful quasars, each representing a different stage in galactic evolution. By examining them side by side, scientists can trace how environment history and cosmic time shaped the growth of gravity's most extreme creations. In this context, Holm 15A became a point of reference, a nearby analog to the luminous beacons that shined from the distant universe. The comparison begins with M87, the central galaxy of the Virgo cluster, located about 55 million light-years from Earth. M87's black hole, famously imaged by the Event Horizon Telescope in 2019, weighs around 6.5. Though immense, it remains far smaller than Holm 15A's, yet its physical nature is the same, a region where light and matter fall inward, trapped by space-time's curvature. Both objects demonstrate how similar processes unfold across vastly different scales. M87's black hole is active, producing powerful jets that stream thousands of light-years into space, while Holm 15A's is dormant, surrounded by quiet starlight. Together, they illustrate the spectrum of black hole behavior from brilliant accretion to silent gravity. Beyond the local universe, quasars such as 10688 reveal what these giants looked like in their youth. 10618, located more than 10 billion light-years away, hosts a black hole estimated at around 60 billion solar masses, inferred from the brightness of its quasar emission. Unlike Holm 15A, 10618 blazes with energy, its nucleus consuming vast quantities of gas as it feeds. The light we see from it was emitted when the universe was less than a quarter of its current age, showing how quickly such masses could accumulate in the early cosmos. The difference between the two is one of time and fuel. 10618 is caught in the act of growth, while Holm 15A represents what remains after the fuel is gone. Their contrast offers a narrative of evolution, from furious youth to tranquil maturity. Other Nearby galaxies also carry black holes of comparable, though slightly smaller scale. NGC 489 in the Coma cluster hosts one around 21 billion solar masses. NGC 1600 in a smaller group holds about 17 billion. Each system lies at the center of its own gravitational domain, a local maximum of mass. The consistency among them suggests that brightest cluster galaxies naturally evolve towards such enormous central objects. The similarities extend beyond mass. All display large depleted cores, smooth light profiles, and ancient stellar populations. These features point to a shared origin through repeated mergers and long-term stability. Holm 15A, NGC 4089, and NG 1600 form a quiet family of titans, the mature descendants of a universe that once burned with quasars. The comparison extends to the physical relationships that connect black holes and galaxies. Decades of research have shown that a galaxy's central black hole mass correlates with properties such as the total stellar mass of the bulge and the average stellar velocity dispersion. This relation, known as the M-sigma relation, appears to hold across many orders of magnitude from small galaxies to large ellipticals. Holm 15A and its peers occupy the upper extreme of this trend. Although they sit slightly above the predicted line, their inclusion reinforces the continuity of the relation rather than breaking it. The implication is that even the largest galaxies follow the same general principles of coevolution. As the stellar system grows, the black hole grows with the mechanisms that feed one also regulate the other. On a cosmic scale, the number of such extreme systems is small. Surveys of clusters across hundreds of millions of light years suggest that only a few dozen galaxies host black holes exceeding 10 billion solar masses. Most are found at the centers of massive clusters where mergers are frequent and gas supplies once abundant. In smaller environments, black holes rarely reach beyond a few billion solar masses because the necessary material for growth is limited. This environmental dependence underscores how deeply galaxy evolution is tied to cosmic structure. Holm 115A's home in Able 85 provided the perfect conditions: a dense cluster core, rich merger history, and deep gravitational potential. In that sense, its existence is not anomalous, but expected, the natural outcome of many galaxies blending their mass into one. Comparing these giants also reveals differences in activity. Some, like M87, continue to emit powerful radio jets, indicating ongoing accretion. Others, including Holm 115A, remain quiescent, radiating almost nothing. The determining factor appears to be the availability of cold gas. Where reservoirs of gas persist, the black hole feeds and glows. Where the gas has been heated and dispersed, it sleeps. Holm 115A's cluster environment, filled with hot rarefied plasma, offers little to accrete, keeping the nucleus dark. In this state, the black hole still influences its surroundings gravitationally, but contributes no significant radiation to the cluster's energy budget. Its stillness may not be permanent. Should new gas clouds fall inward from the intra-cluster, medium activity could resume, but for now, the galaxy remains in balance. Its core a monument to past energy, rather than a source of present life. These comparisons also highlight how diverse the universe's largest black holes can be, invisible yet uniform in nature. Whether blazing as quasars or fading into obscurity, they all obey the same physical laws. Their differences arise from context, how much matter surrounds them, how often they are disturbed, how old their host galaxies have become. Holm 115A stands near one end of this continuum, vast and quiet, while 2 and 6 and 8 marks the other bright and young. Together, they trace a full life cycle formation from collapsing gas growth through mergers, maturity, in equilibrium, and eventual dormancy. The cosmic census of black holes thus becomes a record of time itself. In comparing these systems, astronomers also refine their understanding of the limits of black hole growth. The largest known examples seem to mutter near a few tens of billions of solar masses, suggesting that beyond this point, self-regulating mechanisms prevent further increase. Radiation pressure, limited fuel, and the gravitational structure of galaxies may all impose upper bounds. Holm 15A sits near that boundary, representing perhaps the most massive state a black hole can achieve through natural cosmic processes. If heavier objects exist, they are exceedingly rare or hidden beyond current detection. The study of Holm 15A therefore defines not just an observation, but a limited glimpse of how far gravity can go before reaching its own horizon of possibility. In the quiet of the present-day universe, such giants are difficult to find precisely because they are no longer bright. The quasars of the early cosmos, once visible across billions of light years, have faded into elliptical galaxies like Holm 1. Their energy is now stored, not in radiation, but in gravitational binding, the slow pull that holds stars in place. Each of these massive galaxies is a fossil of an earlier era, carrying within it the relic of primordial fire. By comparing them, astronomers piece together the universe's biography, how it began, grew, and slowed into maturity. Holm 15A occupies the final chapter of that story, where the engines of light have gone silent, leaving behind only the weight of what once was. When viewed alongside its cosmic peers, Holm 15A's enormity is not an outlier, but a clue. It shows that the universe's most massive black holes emerge not from exceptional events, but from the steady accumulation of ordinary ones. Given enough time, gravity turns small differences into vast outcomes. Each collision adds to the total. Each merger writes another line in the history of mass. Across billions of years, the same laws that shape stars and planets work on a scale that spans clusters of galaxies. In that shared pattern from the modest to the immense, Holm 15A stands as one expression of a universal truth that gravity given time builds both the smallest world and the largest abyss. The enormous black hole at the center of Holm 15A commands power that under other circumstances would unleash brilliance. Yet the galaxy's core remains almost perfectly dark. No blazing accretion disk, no visible jets, and no flaring bursts of X-rays betray the presence of a process that elsewhere in the universe lights quasars brighter than entire galaxies. The absence of light does not mean an absence of energy. It means equilibrium. The system has reached a state where gravity still rules, but activity has ceased. The reason lies in the scarcity of available fuel. In younger galaxies, streams of cold gas spiral inward toward the nucleus, feeding the black hole and generating vast amounts of radiation as the gas heats to millions of degrees. In Holm 15A, those reservoirs are gone. The cluster's intracluster medium is hot and tenuous, its pressure preventing the cooling that would allow gas to condense and fall inward. Without a supply of material to accrete, the black hole starves in silence, holding its energy in gravitational form rather than radiative display. This quietness is not unique, but Holm 15A pushes it to an extreme. In galaxies such as M87, faint jets of plasma still emerge from the poles of the central black hole, fueled by minimal inflow of gas. In Holm 15A, even those traces are nearly absent. Radio telescopes detect only a whisper of emission too weak to define clear structures. X-ray observations show no central peak, only a diffuse glow from the surrounding cluster gas. Optical surveys reveal no signs of ionized filaments, no evidence of recent outflows or inflows. The nucleus appears dormant, as though time itself has stopped. This is the natural outcome of billions of years of evolution in a dense cluster environment. As galaxies merge and their gas supplies are consumed or heated, the central engines that once blazed with activity enter prolonged sleep. The black holes remain, but the luminous signatures of their growth fade into memory. The process by which this dormancy arises begins with feedback. During earlier, more active epochs, the black hole likely radiated immense energy, driving jets and winds that heated the surrounding gas. These outbursts counteracted the cooling that would otherwise have fed further accretion, establishing a self-regulating cycle. When heating balanced cooling, the gas stabilized at high temperature, unable to condense. Over time, this regulation starved the black hole, forcing it into quiescence. What remains now is a relic of that earlier interplay, a system in long-term equilibrium where little changes except on billion-year timescales. The surrounding intracluster medium continues to glow faintly in X-rays, a record of the heat deposited by ancient activity. Holm 15A's present silence is the echo of its own past. Even in inactivity, the black hole continues to shape its environment. Its gravitational field maintains order in the stellar motions near the core, keeping the depleted region stable. The galaxy's enormous halo of old stars orbits in slow harmony, guided by the unseen mass at its center. The absence of radiation means that no strong outward pressure disturbs this balance. Stars move according to pure gravity, unaffected by jets or winds. The result is an extraordinary stillness, an entire galaxy poised around an invisible point. It is an image of gravitational serenity, where the same force that once fueled violence now enforces calm. From a thermodynamic perspective, this quiet stage represents a final balance between inflow and outflow. The surrounding gas remains hot enough to resist collapse, but not hot enough to escape the cluster. Small perturbations such as the passage of another galaxy or a minor cooling flow can briefly disturb this equilibrium, sending a trickle of material inward. When that happens, the black hole may awaken slightly, producing short-lived flares or faint jets before returning to rest. Observations of other massive cluster cores show that such flickers occur sporadically, lasting millions of years before fading again. Holm 15A's current quiescence may be only one phase in a repeating cycle that spans cosmic ages. Despite the lack of radiation, the energy contained within the system remains immense. The gravitational potential energy of the black hole is sufficient to power quasars thousands of times brighter than the Milky Way for hundreds of millions of years. The fact that it does not simply means that nature's conditions no longer allow it. The hot cluster gas in hydrostatic equilibrium effectively seals the system. The balance between the pressure of the gas and the gravity of the galaxy creates a stable atmosphere that neither feeds nor drains the nucleus. The state may persist indefinitely unless an external event disrupts it, such as a new merger or a collapse of cooling gas from the cluster's outer regions. For astronomers, this dormancy provides an opportunity. In active galaxies, the glare of accretion often hides the gravitational effects that would otherwise reveal the black hole's mass. In Holm 15A, the absence of emission allows a clean view of stellar dynamics. The light from the stars becomes a tracer of gravity alone, uncontaminated by the chaos of energetic outflows. This clarity enables precise measurements and offers insights into how gravity alone sculpts galactic structure. The galaxy thus serves as a laboratory for the quiet end of black hole evolution, where the interplay of forces reaches near perfect balance. The quiet nucleus also demonstrates how the life cycles of galaxies and black holes are intertwined. When a black hole is young and hungry, it transforms its galaxy through radiation and winds, regulating star formation and shaping large-scale structure. When it exhausts its supply of fuel, the galaxy around it also settles, aging into a diffuse reddish system dominated by old stars. The color of Holm 15A reflects that maturity. Its light is gentle and uniform, devoid of the blue of youth. Every part of it speaks of completion, of processes that have run their course. The stillness we see today is not emptiness, but culmination. Some astronomers refer to this phase as the maintenance mode of cosmic structure. The galaxy continues to exist balanced between forces contributing to the equilibrium of the cluster itself. The hot gas that surrounds it radiates energy, slowly losing heat, at a rate matched by gentle reheating from weak activity or cosmic rays. The black hole, though quiet, remains central to this stability. Its gravity confines the cluster's core, preventing the gas from dispersing. In this way, even without emitting light, it exerts control over the behavior of matter on scales hundreds of thousands of times larger than its own horizon. Seen across cosmic time, Holm 15A represents the late stage in a long transformation from a star-forming galaxy to an active quasar to a silent elliptical. Each phase has its own kind of energy. The early stages glow with radiation. The final one glows with memory. The black hole still contains all the energy of its history stored in the curvature of space-time. The absence of light is simply the visible expression of completion. In this silence lies the ultimate dominance of gravity, not in explosion or display, but in balance. The galaxy shines only with the collective light of its aging stars, while at its heart rests a power so vast that it needs no illumination to declare its presence. Here, energy and stillness are one and the same, and the universe's most violent force reveals itself as perfect calm. Inside Holm 15A, gravity orchestrates a slow, silent motion, though the galaxy appears still when seen from millions of light years away. Every star within it moves through space, along a path defined by the unseen mass at the center. The orbits of these stars are not simple circles, but complex trajectories shaped by the combined pull of the stellar halo and the black hole's deep gravitational well. Their speeds rise toward the core, where the gravitational field steepens, and fall in the outer regions, where the collective mass of the galaxy dominates. These motions, though imperceptible in real time, can be traced through the subtle broadening of spectral lines, each shift a signature of velocity. In the faint light collected by telescopes, astronomers read a silent choreography performed by billions of stars. Within that motion lies the story of how the galaxy holds together, how equilibrium is maintained across distances so large that light itself needs hundreds of thousands of years to travel them. In the outer regions, far from the central core, the gravitational influence of the black hole diminishes, and stars orbit primarily within the collective potential of the galaxy's mass. These outer stars move more slowly, tracing paths that extend for tens of thousands of light years. Their combined light forms the faint, smooth envelope that merges with the cluster's diffuse glow. Closer in, where the mass density increases, the orbits become less regular. The stars move faster, their trajectories distorted by the overlapping gravitational fields of the galaxy and the black hole. The transition between these regions marks what astronomers call the sphere of influence, the radius inside which the black hole's gravity dominates over that of the surrounding stars. In Holm 15A, this sphere spans thousands of light years, an immense region, compared with most galaxies where such spheres are only a few tens or hundreds of light years wide. Inside it, the pattern of motion changes completely. Here, the stars follow orbits that no longer align with the symmetry of the galaxy's shape. Some move in elongated loops, others in box-like paths that bring them alternately close to and far from the center. Each passage near the core feels the pull of the black hole, bending trajectories and accelerating the stars to immense speed. The result is a region of high-velocity dispersion, a measure of how widely the stellar speeds differ. In Holm 15A, this dispersion reaches values above 400 kilometers among the highest recorded. The stars move so fast that they would escape the galaxy altogether were it not for the collective gravity binding them. The energy of their motion mirrors the energy stored in the central mass. Every shift in their velocities, every change in direction, reflects the balance between the desire to fly outward and the insistence of gravity to hold them in place. Despite these violent dynamics, the galaxy as a whole appears in near-perfect equilibrium. The random directions of the stellar motions cancel one another, creating a system that remains stable over billions of years. Collisions between stars are virtually non-existent. The distances separating them are so vast that each one moves as though alone, guided only by the smooth potential of the total mass. The core is a place of great speed, but little interaction. Time here unfolds differently from our everyday intuition. A single orbit near the center might take millions of years. Yet compared with the galaxy's age, such motion is brief. The cumulative effect of countless orbits produces the appearance of stillness when weaned across cosmic distance. Astronomers model these internal dynamics using sophisticated simulations that track how stars respond to gravitational forces. The models confirm that the observed velocity dispersion and light profile of Holm 15A can only be explained by a central mass on the order of tens of billions of solar masses. Without that mass, the stars would not move fast enough to account for the measured line broadening. With it, the entire system achieves consistency. Light motion and gravity align. The data thus provide not only a measure of the black hole's weight, but a confirmation of the underlying physics governing galactic stability. In addition to the stellar motions, the hot gas in and around the galaxy responds to the same gravitational field. Observations in X-rays show that the gas density peaks slightly offset from the optical center, suggesting subtle currents within the cluster medium. These may be remnants of older disturbances, shocks and waves left over from past outbursts of the central black hole. The gas near the galaxy's core is trapped in hydrostatic equilibrium, where its inward weight is balanced by the outward pressure of heat. This balance mirrors the stellar dynamics on a slower time scale. Gas motions occur over millions of years, while stars trace orbits lasting hundreds of millions. Yet both reveal the same gravitational architecture, a nested system of forces converging toward the dark heart at the center. Occasionally, small amounts of gas may cool and drift inward, crossing the boundary of the sphere of influence. When this happens, friction and compression can cause the gas to heat and emit faint X-rays before disappearing from view. These brief flashes of energy offer hints that accretion, though minimal, has not entirely ceased. The black hole remains connected to its environment through these slow, subtle exchanges. Each inflow of matter adds an imperceptible amount to its mass, ensuring that the process of growth, though now nearly halted, never truly ends. The rate is so low that it would take trillions of years to double the mass. Yet in the universe's language of deep time, even such glacial progress contributes to continuity. Within the sphere of influence, the combined gravitational field shapes not only motion, but geometry. Space itself is curved, and the paths of light from background galaxies bend slightly as they pass through the region. Though too small to produce strong gravitational lensing like that seen around entire clusters, this subtle deflection can in principle be detected with precise instruments. It adds one more layer to the evidence of the invisible mass, confirming that gravity alone sculpts the environment. Every photon passing near the core carries a trace of that curvature, a faint record of how space and time respond to the presence of concentrated mass. In such systems, equilibrium is fragile but enduring. The random kinetic energy of the stars prevents collapse while the collective gravity of the galaxy keeps expansion in check. Small disturbances, such as the tidal pull of nearby galaxies or fluctuations in the cluster medium, ripple through the structure but rarely destroy its balance. Over billions of years, these motions smooth out, leaving a configuration that persists almost unchanged. Holm 15A has reached that state. Its stars orbit in quiet disorder. Its gas rests in hydrostatic calm, and its central black hole anchors both. The system has no sharp edges or discrete boundaries. It grades gradually outward into the cluster's light. Gravity has molded it into a self-sustaining whole, where the inward pull of mass and the outward drift of motion are exactly matched. Seen from afar, the galaxy's luminous halo and faint center might suggest emptiness. But in truth, the heart of Holm 15A is alive with motion that no eye can see, yet that defines its every feature. Every photon of light that reaches Earth from this galaxy has passed through fields of force, through zones of curved space, through a web of orbits interlocked by gravity. It carries the story of a system perfectly balanced between stillness and movement. The central dynamics of Holm 15A reveal not chaos, but harmony, the unending conversation between matter and mass that keeps the universe intact. In this balance lies the essence of cosmic structure. Everything moves so that on the grandest scales, everything can remain still. Beyond the stellar envelope of Holm 15A lies an even larger and more diffuse realm, the intracluster medium of Abel 85. Here, matter no longer takes the form of stars, but of ionized gas, so hot that it glows only in X-rays. This plasma fills the spaces between galaxies, bathing the entire cluster in a vast halo of energy. The temperature of this gas reaches tens of millions of degrees, high enough to strip electrons from every atom. What appears as emptiness and visible light is in truth a dynamic environment of heat pressure and slow motion. It is the atmosphere of the cluster sustained by gravity and shaped by the galaxies that move within. In this invisible ocean, Holm 15A floats at the center, surrounded by waves of gas that extend for millions of light years in every direction. The relationship between the galaxy and this hot medium is intimate. Each regulates the other's behavior across cosmic time. X-ray telescopes orbiting Earth have mapped this halo in remarkable detail. Images from observatories like Chandra and XMM Newton show that the gas around Able 85 is densest near the cluster's center, where Holm 15A resides. The brightness of the X-ray emission decreases gradually outward, tracing the distribution of mass in the cluster. At the very center, a small depression appears, a region slightly cooler and less dense than its surroundings. This feature marks the point where the black hole's past activity once pushed back the gas, creating cavities known as bubbles. Although those bubbles have long since faded, the texture they left behind remains visible in temperature and density maps. Such features are the footprints of energy released by the black hole in earlier epochs, when it still accreted gas and expelled it through powerful jets. The surrounding medium preserves these relics like fossils embedded in light. The gas within the cluster is held in a delicate balance between cooling and heating. As it radiates energy in X-rays, it slowly loses heat and would, if left alone, begin to cool and sink toward the center, potentially feeding the black hole. But the energy from periodic outbursts, both ancient and recent, counteracts this process. Even faint feedback from the dormant nucleus can stir and warm the plasma enough to prevent runaway cooling. This self-regulation is a hallmark of galaxy clusters. In systems without such feedback, dense cooling flows form, producing bursts of star formation in the central galaxy. In Able 85, the near absence of young stars shows that the heating has matched cooling for billions of years. The hot gas remains suspended in equilibrium, glowing softly but never condensing. The composition of this plasma reveals the history of countless stars. Spectral analysis shows that it contains not only hydrogen and helium, but also heavier elements such as iron, oxygen, and silicon. These were forged in supernova explosions long ago and expelled into the cluster medium, where they now drift freely. The abundance of these elements provides evidence that the galaxies of Able 85 have been enriching the cluster for billions of years through their life cycles of star birth and death. In this way, the intracluster medium acts as a record of stellar history on a collective scale. Every atom of iron once resided in the heart of a star. Every photon of X-ray light now carries the memory of that transformation. The dynamics of the gas can also be traced through its motion. Subtle shifts in X-ray spectral lines indicate turbulence within the medium, driven by galaxy motions and past merges. These eddies distribute heat and mix elements, preventing the gas from cooling unevenly. The central region around Holm 15A is comparatively calm, though not perfectly static. Slight asymmetries in the temperature map suggest the lingering effects of small infalls or weak shocks. These are the faint aftershocks of cosmic structure formation, echoes of the time when smaller groups of galaxies merged to form Able. Even now, gravity continues to draw in matter from the outskirts of the cluster, maintaining slow but steady evolution. Holm 15A's black hole interacts with this hot atmosphere through gravity, and on rare occasions through energy release. Although currently inactive, it still shapes the surrounding gas by anchoring the cluster's potential well. The gas near the center is compressed by the galaxy's mass, reaching higher density and temperature. If accretion resumes, the inflowing gas will radiate energy as it falls inward, possibly reigniting faint X-ray or radio emission. Such episodes are cyclical, repeating over billions of years. Each phase of activity creates new cavities and waves in the gas, while each period of quiescence allows the medium to settle again. Holm 15A now rests in one of these quiet intervals, yet the signatures of past outbursts remain etched into the cluster structure. Observations of similar systems support this picture. In the Perseus and Virgo clusters, for example, jets from active black holes have carved enormous voids in the surrounding plasma, displacing venons of solar masses of gas. 85 shows smaller but analogous features, implying that Holm 15A once generated comparable energy. The difference is time. The activity has long ended, leaving behind only the softened contours of its effects over cosmic durations. These interactions serve as a form of feedback control. The black hole prevents the gas from cooling too quickly, while the gas, by limiting the supply of fresh fuel, keeps the black hole from overfeeding. The two systems sustain each other's stability, ensuring that neither collapses nor explodes. The pressure of the intracluster gas also affects the galaxies themselves. As smaller members of Abell 85 move through this medium, the gas strips away their outer layers in a process known as ram pressure stripping. Their star-forming material is removed, and their evolution accelerates toward quiescence. Over time, this mechanism enriches the cluster center with old gas-bore galaxies, while contributing additional elements to the plasma. The environment thus reinforces its own maturity. Holm 15A sits at the focal point of this process, the final collector of the cluster's long gravitational history. Even though this gas is invisible to human eyes, it contains the majority of the cluster's ordinary matter. The stars of all the galaxies combined account for only a small fraction of the total mass. The rest resides in this hot, glowing medium. The gas's faint but pervasive presence makes it a dominant factor in the cluster's structure. It forms the bridge between galaxies, the material that fills the vast distances where gravity still binds, but light rarely shines. Within it, magnetic fields thread through space, shaping the motion of charged particles and guiding subtle currents that can persist for eons. Holm 15A's gravitational pull confines this magnetic web, ensuring that the cluster remains coherent even across millions of light years. At the largest scale, the balance of heat, gravity, and motion in the intracluster medium mirrors the balance inside the galaxy itself. Each component, stars, gas, and dark matter, plays its role in maintaining stability. The black hole, though dormant, defines the anchor point for all. The gas, through diffuse, provides the medium through which that gravitational influence extends. Together they form a single continuous system from the black hole's event horizon to the outermost edges of the cluster. The hot gas of Abell 85 is not an afterthought, but a vital expression of the same gravity that carved Holm 15A's core. Its glow is the cluster's faint heartbeat, sustained by the same forces that once ignited stars and now hold them still. In its quiet radiance, the universe shows how energy, once released in violence, can settle into lasting calm, and how even in emptiness, the traces of creation and the story of Holm 15A begins not with the galaxy itself, but with the universe that made it possible. More than 13 billion years ago, matter distributed by the Big Bang began to clump under gravity, forming the first small galaxies in a young, denser cosmos. These early structures, composed mostly of dark matter halos and clouds of hydrogen, merged repeatedly to create larger systems. The process was hierarchical. Small fragments combined to form larger ones. And over cosmic time, These mergers gave rise to the massive clusters and galaxies seen today. Able 85, the cluster that now hosts Holm 15A, was assembled through this long sequence of coalescence. Its present form is the result of billions of years of slow gravitational accumulation, during which every merger added both stars and dark matter to the growing core. Holm 15A emerged as the final product of this accumulation, a galaxy that inherited the combined mass of many ancestors. In the early epochs, gas within these forming galaxies was cold and dense, collapsing under its own weight to form the first stars. Supernova explosions enriched the surrounding medium with heavy elements, while radiation from young stars and nascent black holes heated the gas and regulated further star formation. Each merger triggered new waves of star birth, lighting up the universe with brief, brilliant phases. But as the galaxies grew larger and their central black holes became more active, this pattern began to change. Powerful radiation and outflows from accreting black holes heated and dispersed the gas, reducing the availability of material for new stars. Gradually, the galaxies shifted from blue star-forming systems to red quiescent ellipticals. Holm 15A represents the end point of that evolution, the stage where star formation has long ceased, and the entire system glows with the subdued light of old stellar population. At the cluster scale, the growth of Able 85 followed the same logic. Smaller groups of galaxies fell together, drawn along filaments of the cosmic web. Collisions between clusters heated the intra-cluster gas, raising its temperature to tens of millions of degrees. This hot plasma slowed the rate of future mergers by providing a cushion of pressure around each system. In this way, the cluster evolved toward equilibrium, and Holm 15A, forming at its center, grew from the combined remains of many smaller galaxies drawn inward by the cluster's gravity. Each infell added mass to its halo and stars to its envelope. Some of these galaxies were destroyed entirely, leaving behind only faint streams of stars that now orbit invisibly within the cluster's diffuse light. Others survived partial disruption, their cores merging directly into Holm 1. Over time, this process erased individual identities, replacing them with the single enormous structure that dominates the cluster today. The growth of the central black hole paralleled this accumulation. Each major merger brought a new supermassive black hole from an infalling galaxy. After the galaxies merged, the two central black holes spiraled inward under the influence of dynamical friction, forming a binary system. The pair shed energy through gravitational interactions with surrounding stars, ejecting them from the core and expanding the central lightless region. Eventually, the black holes merged, releasing a burst of gravitational waves that carried energy away and allowed the resulting single black hole to settle at the center. Repeated many times over billions of years, this process produced the vast cavity seen today and built the black hole to its extraordinary mass. The present structure of Holm 15A's core is a fossil of these ancient mergers, a scar left by the repeated coalescence of invisible giants. During the intermediate stages of its formation, Holm 15A likely passed through periods of intense activity. As gas from merging galaxies funneled toward the center, the black hole would have fed rapidly, shining as a quasar visible across the universe. Outflows and jets from this active nucleus would have shaped the surrounding gas, driving shocks into the cluster medium and altering the rate of cooling and star formation. Each outburst injected energy into the environment, helping maintain the long-term balance observed today. The faint cavities in the cluster's X-ray emission are remnants of such episodes. They show that even in the distant past, feedback between the black hole and its surroundings operated to regulate growth. When the supply of cold gas finally diminished, the activity subsided, leaving the quiet, massive elliptical seen today. The timescales involved in this transformation stretch across the entire history of the universe. The first progenitor galaxies that eventually formed Holm 15A began merging when the universe was less than 2 billion years old. By 6 billion years, the system had grown into a large elliptical with an already massive black hole. By 10 billion years, most major mergers had ended, and the galaxy settled into its current form. Over the remaining time, only minor accretions and gradual dynamical evolution altered its structure. The black hole's mass increased slowly through the capture of small amounts of gas and stars, but its main growth phase was complete. Today, Holm 15A stands as a record of cosmic history, a structure whose very size encodes the passage of time and the accumulation of matter from an expanding universe. This long chronology shows how the fates of galaxies and black holes are interwoven. Without mergers, Holm 15A could never have reached its present scale. Without feedback from its black hole, it could never have achieved stability. Each phase of its evolution depended on the balance between growth and regulation. Early in its life, gravity gathered. Later, energy released from accretion countered that gathering. The result is not a runaway collapse, but a self-stabilized system, one that has maintained equilibrium for billions of years. Even now, the faint X-ray glow of the cluster gas and the gentle motion of stars reflect that balance. The violence of formation has given way to the stillness of maturity. In studying Holm 15A, astronomers glimpse the broader evolution of cosmic structure. Every galaxy cluster undergoes similar processes, though few reach such extremes. The patterns seen here, early collapse, merger-driven growth, black hole feedback, and eventual quiescence, describes the universe's own progression from chaotic youth to ordered calm. In this sense, Holm 15A is not an exception, but a culmination showing what happens when cosmic processes are allowed to continue unhindered for the full span of time. Its immense mass, faint core, and dormant nucleus are the natural outcomes of gravity's long work. The story of its formation is still being refined as new instruments probe the faintest reaches of space. Radio arrays detect relics of old jets. X-ray maps reveal the temperature structure of the cluster gas. Optical surveys measure the motions of galaxies still falling toward the core. Each observation adds another layer to the narrative. Together, they confirm that Holm 15A is the mature product of a universe governed by gravity's patient persistence. Over cosmic time, energy has shifted from motion to heat, from radiation to mass, until the system reached a state of enduring balance. The galaxy's present calm is not the absence of activity, but the final expression of equilibrium, a quiet monument built by time itself. Even with the remarkable data gathered from the largest telescopes on Earth, Holm 15A continues to challenge astronomers. Measuring something invisible at a distance of hundreds of millions of light years will always carry uncertainty. And the case of this galaxy illustrates the limits of even our best methods. The true mass of its black hole remains a range, not a single figure, perhaps 20, perhaps 25 billion solar masses, depending on the assumptions about geometry, inclination, and orbital anisotropy built into the models. Each refinement narrows the uncertainty, yet no measurement can be entirely free from it. Observing motion in such a faint, diffuse core requires precision that approaches the edge of current capability. Even the most advanced instruments blur the inner few hundred light-years, forcing scientists to reconstruct what happens there from indirect evidence. The difference between a spherical and triaxial assumption, or between isotropic and radial stellar orbits, can shift the derived mass by billions of solar masses. These limits do not invalidate the result. They define the frontier of measurement, the place where observation meets the fundamental precision of nature itself. One major source of uncertainty lies in how stars move within the flattened, elongated structure of the galaxy. In real space, the stars of Holm 15A do not orbit in neat circular paths, but in a mixture of loops, tubes, and chaotic trajectories. Some models assume that the motions are evenly distributed in all directions. Others allow for preferences, more radial or more tangential movement. These differences affect the way projected velocities appear from Earth, since observers see only the component of motion along our line of sight. The true three-dimensional structure must be inferred. Triaxial models, which accommodate the full complexity of orbits, are now considered the most accurate, but they still rely on assumptions about how light translates to mass. The stellar mass-to-light ratio, a key parameter, depends on the age and composition of the stars, which cannot be known precisely. Even a small adjustment in this ratio changes the inferred weight of the black hole. Another limitation arises from the contribution of dark matter. In the central regions of massive galaxies, stars dominate the gravitational field, but beyond a certain radius, dark matter becomes significant. Determining where one influence ends and the other begins is difficult. If the dark matter distribution is steeper or shallower, then assume the total mass assigned to the black hole shifts accordingly. Holm 15A's diffuse structure makes this distinction even more complex because the galaxy blends gradually into the cluster's dark matter halo. The boundary between the two is theoretical, not physical. For the most massive systems, this blending means that viewing the black hole's mass is inseparable from understanding the larger gravitational context. Each new observation forces a reconsideration of how these components interact. The distance to Abel 85 also introduces a small but unavoidable margin of error. A few percent difference in distance translates directly into a few percent difference in derived mass. The cluster's redshift provides a reliable estimate, but peculiar motions, those due to local gravitational tugs rather than cosmic expansion, can add subtle corrections. These uncertainties may seem minor, but when multiplied by billions of solar masses, they become substantial. As a result, all quoted masses for Holm 15A include significant error bars. The range between 20 and 40 billion solar masses does not reflect disagreement so much as the inherent challenge of observing a system so vast, faint, and distant. Beyond the technical questions lie broader theoretical ones. What sets the upper limit on black hole growth? Why do some galaxies, like Holm 15A, produce black holes that reach tens of billions of solar masses, while others stop at a few billion? Current models suggest several possibilities. In the densest environments, repeated mergers in abundant gas can accelerate growth early in the universe's history. But feedback jets, radiation, and winds eventually regulates the process, preventing runaway accretion. There may also be limits imposed by physics itself. When a black hole grows too massive, the surrounding gas cannot cool efficiently, reducing the supply of infalling matter. For Holm 15A, these mechanisms appear to have reached balance. Its black hole no longer grows rapidly, nor does it radiate enough to alter the cluster environment. It has arrived at a natural endpoint, a state of near equilibrium, where growth and feedback cancel each other over cosmic time scales. Some scientists question whether there might exist black holes even larger than Holm 15A, hidden in distant or obscured regions of the cosmos. Quasars from the early universe hint at objects exceeding 60 billion solar masses, but those estimates are indirect, based on the luminosity of accretion rather than on measured dynamics. Direct dynamical confirmation like that achieved in Holm 15A remains rare because of the observational challenges. Future instruments such as the next generation of 30 and 40 metaclass telescopes will extend these capabilities, resolving stellar motions at greater distances and fainter brightness. With them, astronomers hope to test whether Holm 15A represents a unique case or simply the most visible member of a hidden population of extreme systems. There are also questions about stability. How does such a diffuse galaxy maintain coherence around a single central point of gravity without collapsing or fragmenting? The answer appears to lie in the balance between dark matter and stellar pressure. The random motions of stars provide an effective pressure that counteracts gravity, while the dark matter halo supplies an extended cushion of gravitational potential. Together, they create a long-lived equilibrium, one that can survive billions of years without significant change. Yet small instabilities might still exist. The asymmetries observed in the velocity field of Holm 15A suggest that the system continues to relax from past merger. The time scale for such relaxation is immense, longer than the current age of the universe, implying that cosmic structures of this scale evolve in near perpetuity. Another ongoing inquiry concerns the precise shape of the galaxy's light profile. While most ellipticals follow predictable mathematical forms, Holm 15A's brightness declines unusually slowly, with radius merging seamlessly into the cluster's background light. This makes it difficult to separate the galaxy from the intracluster component, a distinction necessary for defining total mass and size. Photometric analyses attempt to fit both components simultaneously, but the results depend on how the transition is modeled. This uncertainty influences not only the derived mass of the galaxy, but also the fraction of stars that truly belong to Holm 15A versus those orbiting freely within the cluster. The line between galaxy and cluster is blurred. Another reminder that cosmic boundaries are rarely sharp. Despite these ambiguities, the overall picture remains consistent. Holm 15A is a product of mergers and long-term evolution within a rich cluster environment. Its black hole ranks among the largest known at stellar core, among the most depleted in its structure, among the most diffuse. Each observation refines but does not overturn this understanding. The remaining questions are not about whether such a galaxy can exist, but about the details of how it came to be and how its equilibrium is maintained. These are not failures of measurement, but signs of a mature science approaching the edges of what can be known. At these limits, astronomy becomes an art of inference. Researchers must piece together a picture of reality from partial evidence, balancing light, motion, and theory in a single consistent framework. Holm 15A sits at the boundary of that framework, testing the reach of our methods and the scope of our imagination. It stands as both an achievement and a challenge, proof that we can weigh the invisible, yet also a reminder that beyond each measurement lies another horizon of uncertainty. In its faint glow, the universe shows us not only what is known, but what remains to be discovered. The delicate line where precision meets mystery. Good